Alright, exercise 33. So, the way we're going to prove this is first we're going to fix B and R, define G such that Gx is equal to fx minus for x less than b, and g of x is equal to f of b for x greater than or equal to b. Here, fx minus is just, let's see here, that's the limit as x increases. So it's the limit as a increases to x of f of a. And so then g is increasing as well. GB minus GA is less than or equal to f of b minus f of a, and G prime equals f prime almost everywhere on, let's see here, from A to B. Does that include B? Yeah, it's just a point, doesn't matter. By Theorem 3.23b. Now, I want to take a little bit of a minute to explain. This is kind of a strange way to define G, or at least it's a little bit counterintuitive, because one of the things that we're really after is this G prime equals f prime. And we know that by 3.23b, if you have an increasing function f and you define g in this way, then the two functions will have the same derivative almost everywhere. That would be on the real line, but because g is equal to fx minus in this region, then we know that g prime equals f prime almost everywhere in this region, because that's the only region where we can really apply 3.23b. Now, I guess I should make this open, because technically, because g is only defined in this way for x less than b, so Theorem 3.23b doesn't technically apply if we're not considering this region. But anyways, hold on. So yeah, but then there's another thing here, and that's that we had to fix b beforehand and define g in this way for larger x. And that seems a little strange at first, but what we're really going after here is this inequality, because this inequality is really the key that's going to give us this final inequality here. And we know we want this to happen so that we can apply that g prime equals f prime almost everywhere, and that all that is good. But this inequality would give us, let's see here, knowing this gives us g of a, let's see here, it tells us because f is increasing, g of a is going to be greater than or equal to f of a. So minus g of a is going to be less than or equal to minus f of a. So that's good, but what you need to get is you need to get this inequality. You need g of b to be less than or equal to f of b. And if you were to define define g like this on the entire real line, then these two things might not hold. It could be the case that fx minus is actually greater than or well, this is true. F of x minus is greater than or equal to f of x, and that's because f is increasing. And so this inequality, you wouldn't be able to say this inequality if you just define g to be fx minus everywhere. So what you have to do is you have to fix the b and kind of use that as a cutoff. So when you're less than b, you define it in the way that you would like to, but when you're greater than b, you define it like this, so that you get this inequality here. So that's just a little intuition about why we're doing this. So now g is increasing. So then there exists a unique Borel measure mu g on R such that, and of course the such that is taken into this exists symbol. So there exists a unique mu g on R such that mu of g of x comma y is equal to gy minus gx for x less than y. And this holds for all real numbers. Because, let's see here, g is constant past b. So, in particular, it's increasing. Or it's not decreasing. So, let's see here, mu g and the Lebesgue measure are sigma finite, and the Lebesgue measure is a positive measure. So, by Ratana, or, these Folland kind of defines these theorems in sort of a weird way, so I get a little confused as to if we're applying like Ratana or if we're just doing like a decomposition of these measures. But so I'm just going to say, just to be safe, buy the textbook, because that way I can't possibly be wrong. Well, I mean I can, but I'm less likely to be wrong. But anyways, you can write d mu g equal d lambda plus f d mu, f dm, for some complex measure, lambda, and some f in L1m, such that lambda is mutually singular with respect to the Lebesgue measure. Now, this next thing you might have to go back and check, but in the proof of Ratana, and now that I think of it, this is actually using the Ratana theorem, because we actually are looking at the proof here. So, in the case of nu and mu positive and finite measures, we said, how do we get lambda? We set d lambda equal d nu minus f d mu, where f is an element of the collection of functions here, such that the integral of f d mu is less than or equal to nu of e for all e in M. And so if you remember how this proof went, what we did was first we considered the case of nu and mu positive finite measures, and then we extended to the case of sigma finite, and then we extended to the case of signed and complex, depending on which section you're looking at. I'm pretty sure this is using the original Ratana, in which case we're looking at the signed case, but well, maybe not. Whatever the case, what we're dealing with here is positive measures. So in this case, we defined, because of how we've defined this, look, integral of e of f d mu is less than or equal to nu of e for all e. And so if we look at this thing on the side, on this right hand side here, we're taking nu of e and we're subtracting this integral. which we know is less than or equal to nu of e. And so that tells us that lambda is a positive measure, or yeah, and that's really important because that's going to give us our inequality here. So, and then let's see here, the case of nu and mu positive and sigma finite followed from writing our space X as a union from 1 to infinity of X ends, disjoint union, where, I'm going to have to scroll down a bit, where we've got mu of each xn and nu of each xn are both finite. And we set lambda equal to the sum from 1 to infinity of the lambda n, where each lambda n was obtained by doing this same thing but on xn. And so lambda is positive in this case as well. And then let's look to the lambda that we got here. Well, look, mu g is sigma finite and positive, and Lebesgue measures sigma finite and positive, and so then lambda, by this logic, is going to have to be positive. So, hence, in our problem, lambda is a positive measure. Alright, I just had to go back and check something real quick. So, by Theorem 3.22, let's see here. For Lebesgue, almost every x in R, we have, see here, I'll write this a little bigger. Limit as h decreases to 0 of g of x plus h minus gx over h. Now, we don't quite know that this limit exists per se, but it's kind of obvious once we keep writing it out. This is equal to the limit as h decreases to 0. Well, this thing on top here is just mu g of, let's see here, we've got x plus h divided by the Lebesgue measure of x plus h, because that's just going to be h. And so, what is this? But this is just equal to f of x. And here's where we're using 3.22. It's to say that f of x is equal to the limit of this fraction almost everywhere. So we have this, and we also have, let's see here, the similar thing but increasing. So let's write out what this is. Gx plus h minus gx over h. This is equal to the limit as h increases to 0, mu g of, this turns out to be x minus hx over, again, x minus h x. And that's because what you want to do is, because h is increasing, you want to flip these and then write in this form. And basically it works like this. This is equal to f of x. So what does this mean? This means that g, but then now that we know that this limit exists, we know that this is, since these two limits exist and they're equal, these two limits exist and they're equal, meaning that they're equal to g prime of x. So so basically what I'm saying is g prime is equal to f, Lebesgue, almost everywhere. Thus, we can finally do our string of estimates, and we get fb minus fa greater than or equal to gb minus ga. This is way from the beginning. Then we just write this in terms of mu sub g. But then what did we say mu sub g was? We said that that's just d mu g is d lambda plus the integral over this region of f dm. But lambda is positive, and so this is going to be greater than or equal to the integral over this interval. I'm just going to write it integral from a to b f dm. But then we know that f is equal to g prime Lebesgue almost everywhere, and so their integrals are equal. And of course, we also know from way from the beginning that g prime is equal to f prime Lebesgue almost everywhere. So f prime dm. And that should do it. That's the end of the exercise.